Yeah.
So the first question of the homework asks gain or loss of energy.
Yeah.
And like the theory actually goes up.
Yeah, they mean gain or loss of potential energy, I think.
Okay.
They're not being clear. So what would you say now?
It went up to gain potential energy.
Yeah.
But it's like
It's not clear.
and it's using a lot of energy.
It's not clear. It's not clear. They should have been clearer. He meant to ask you, does it gain or lose potential energy? Okay. Right, we'll start the next lesson now. Can you look up power and efficiency?
I don't know, I cannot upload.
Well, did you put the two videos in the folder?
Yeah, but it's not upload.
Maybe it won't upload on the Griffith College Wi-Fi. Maybe it's blocked.
Yes, so.
Can you still use OneDrive on Griffith Wi-Fi, or is it blocked? You don't know. But it doesn't matter. Do you have them in the folder?
Okay, do you have USB?
Yeah, but can't you just copy the video and paste it into the folder? Do you know what I mean?
Yeah,
Like, where's the video?
because my video on the here.
Yeah. Yeah, where is it? So, there. Oh,
Sorry.
there. So can't you just go back? No. Close that. Go back. So like, can't you just take this and like move it, copy, paste,
It's just a share.
share?
Yeah, then choose the one word.
No. Not share like this. X, close that.
Just sit down and know what to do.
Save to files. Where's the folder we made?
Because they don't show the on one drive.
Why not?
I don't know.
Oh,
Maybe I can show it on
there's OneDrive.
Yeah.
It's like on my street, I was just serving you with student discount.
What's happening?
Because it is upgrading.
You know when you come up from our school, like,
Clean.
Preparing.
Yeah.
Ah.
Okay. I hold here is a way to your radio.
Huh?
I put on here to your radio.
I don't like apples. All right. Can we continue now? Power and efficiency. Now, imagine you carried 1 kilogram up a hill. Now imagine 1,000 ants, each carried 1 gram up the hill with you, one by one. On the top of the hill there are 2 piles, your 1 kilogram and the ants' 1 kilogram. Who did more work? No, it's the same amount of work. Because in both cases 1 kilogram has been moved up the hill. But there is a little bit of a difference here. The ants would have done it more slowly. So not only does it matter the work that you're doing, but also how quickly you can do it. And this is the point of this lesson. This gives us the idea of what power is. So power isn't just work, it's how quickly you can do your work. So power is the work done per unit time. And as a formula, what would that be? Yeah. Okay. Got that? Now, we call the units joules per second, but there is another unit that could be used. Does anyone know? Yeah. 1 watt of power is 1 joule of work done in 1 second. Got that? Yeah? Okay. Next. When you convert electrical energy into light energy, you have not used any energy. You've converted it. But the electrical energy was converted into light, which you want, and heat, which you don't want. So my question is, for a 100 watt light bulb, that means per second there's 100 joules of work being done. Now, just a normal old light bulb, not a new light bulb, an old-fashioned light bulb. I want to know what you think is how much work was the light and how much was the heat. So in the 100 watts, how much do you say was actually light work and how much was heat work? So what do you think? I'll get everyone's opinion. So, what do you think? How much was light and how much was heat? Son, we'll start with you. What do you think? Just your opinion. For just an old-fashioned light bulb, a 100 watt light bulb, how much do you think was light and how much do you think would be heat in 100 watts? 100. Okay. Listen, everyone, listen. I have an old-fashioned light bulb. It's 100 watts. So in 1 second, how much work? 100 joules in 1 second. Okay. How much of that do you think was light and how much of that do you think was heat? So I have one answer. You think 50-50, was it? 50 joules light and 50 joules heat. Okay. Any other one? Yeah, what do you think? Which way? 70 light and 30 heat. Okay? You're going 70-30 as well. Or 80-20, okay? 50-50?
I'm not sure if I say it's like it's both of them are 100 like switching like
What?
like it's
I'm just
light.
looking. No, man, I'm just looking for a number. I just want a number. How much was light and how much was heat? Nothing fancy. You think the light should definitely be more than heat. Okay, so you're going with 80-20 in favour of light. Okay. Aoife, what do you think?
I think the heat is more than that.
So what number would you give it? 20-80, the other way? Yeah, okay, good. What do you think? 50-50. 50-50. 40, 40-60? Okay, so you're all way off. Okay, it is 99-1, and the 99 is the heat. Yeah? So 99 joules will be heat and 1 joule will be light. Okay? This is for an old-fashioned light bulb. Now the situation improves with the newer light bulbs, like the LED light bulbs. They would be more in proportion of more light than heat then, okay? But an old-fashioned light bulb would be 99-1. So, this gives us our next idea, which is what's called efficiency. How much energy is really for the job we want, and how much is wasted. Okay? So, efficiency is a percentage. It's the percentage of useful over input. So as a formula, efficiency is useful output over useful input times 100. And you can use energy, or you can use power. You can write it using energy or power. Both formulas work.
Energy. Okay.
You got that?
No.
You got that?
Wait a moment.
Okay. Now look, I say there, ideally you want the efficiency to be 100%. But because of heat loss and other reasons, it's never 100%. It's always less than 100%. There is one thing in your home that might be close to 100%. So what thing in your home do you think is closest to 100% efficiency? Well, we know it's not a light bulb, that's for sure. TV, I'd say it's about... No, I'd say TV is pretty low. I'd say TV is about 25% efficiency.
Yeah.
Maybe the newer TVs might be better. About 25%, I would say. PC? PC is actually worse than the TV. PC would only be 10% efficient. Anything else? Huh? No, I'd say that's about 50. Microwave would be pretty good. Yeah, I wouldn't say it's near 100, but it'd be pretty high. No, because a lot of heat leaks out of the oven. Well, out the door. Yes. Okay, iron. Iron wasn't the one I was thinking of, but that'd be close to 100. What I was thinking of was just an electric heater. Because think about it. There's no such thing as heat loss in an electric heater, because you want the heat to come out anyways. So what is the wasted energy in the electric heater? What is the form of energy that is coming out of the electric heater that you don't want? Sound. A little sound. A little sound and a little light. You know when you see it glow, you don't really want the light, you just want the heat. So I would say an electric heater is probably 99% efficient. I'd say. Okay. Most things aren't this high. So yeah.
I heard that like sound waves are converted to heat after they come out of that source. But like, is it true? Like, do they actually
Sound waves would
convert to heat?
would convert the heat, yeah. Yeah, a little bit, yeah.
Or like the heat is not much felt, like it's not really felt, but like
Oh, it's very small. Because sound has very little energy. You know, as I'm speaking to you, 5 or 6 watts. If I'm talking loudly, maybe 10 watts would be the energy output. So a 10 watt heater is not going to warm up anything, is it? Like heaters are usually thousands of watts, like 2,000 or 3,000. So you're not going to, as you said, you're not going to feel it. But no, technically it would become heat as the next form of energy. Okay. A boy lifts a 2 kilogram physics book off the ground of a height 1.1 meter. It takes him 2 seconds to do this. What is the power in his arms? Okay, so firstly, what's the formula for power? Work over time. Do we know the time?
Yes.
Yeah, okay. So next question is, what formula do we need to use for work? What type of work is he doing? Yeah, or another way to think about it is, he is given the book potential energy. Isn't he? The book is initially on the ground. How much potential energy does it have? 0. When you raise it, now it has potential energy. Where did it get that energy from? From his, yeah. So, I would say for this one you could use the formula mgh over T. Right, tell me what you get. What is it? So about 11, roughly, what's the unit? What? Right, part 2. He got his energy from his breakfast. However, half the energy is wasted, I should say, as heat. What is his power now? So, what's the efficiency here? 50%. I think that's fine. Yeah, that's hard work. Builds up heat. Sweating profusely as you're lifting your physics book. He's wasting energy because he's producing heat. Like when, okay, I know 2 kilograms isn't really heavy, but you get the idea. If you're lifting up a heavy weight, the heat your body generates, that's waste. Because you want to lift the weight. You don't want to lift the weight and slightly heat up the room. You know? So, if the efficiency is 50% now, what's the power? So, formula, 50% equals output over input times 100. Yeah? Right, so use that formula to tell me what the power is now. Yeah. It's about 22. Okay? Now you have to be careful. What is the output here? It's still 10.8. The input is now different. We don't know what the input is. That's what I want you to work out. Now this makes sense if you think about it. Will his arms need to be more or less powerful if he is less efficient? His arms will need to be more powerful. Or think about it like this. Suppose that heater is heating up the room. It has a power. Let's say it's 1,000 watts. Okay? Now, suppose now something happens to the boiler. The boiler breaks. And now the boiler is only working at 50% efficiency. Okay? If I want the same heat in this room, will I need to turn the boiler up or turn it down? I'll have to turn it up. It's the same logic here. If now the boy is less efficient, then his arms will need to be more powerful, not less powerful. Okay? Continue? Yes? Yeah? Well, look, let's have a look at another one. A 1,200 kilogram car starts at rest and reaches a speed of 100 kilometers an hour in 10 seconds. If the car was 100% efficient, then what is the power? Okay, so before we start, what's the formula for power? Work over time. And in this case, what would be the formula for work? No. That's force. A half mv squared. Do we know the m? Yeah. Do we know the v? Yeah, although we'll have to convert it. And do we know the time? So, give me the power. Right, do you have the first part? What did you get for the power? What did you get for the power?
6,206.
So it'd be, if we use kilowatts, it's about 46 kilowatts. Yeah, that sounds like a reasonable value for the engine. But of course, it's 100% efficient. Is that realistic? No, of course not. The car, more realistically, would be 40% efficient. Now wait, before you calculate this, if you now discover the car is only 40% efficient, but it still does the same thing, that is, it gets to a speed of 100 kilometers per hour in 10 seconds, does that mean the car engine was more powerful or less powerful? More. Because it has to now overcome its inefficiency. So, what did you say the first time it was? 40... What was it previously? 46.2 kilowatts. Okay, give me the answer for the next part now with the 40% efficiency. It should be a bigger number. Did you get it? Did you get the first part? How did you not get the first part?
Teacher, can you detail for the first?
Yeah, okay, look, let's look at the first part here. Right, so for the first part, power equals work over time,
Yeah.
right? That's a half mv squared over t. What's a half the mass? 600. And the time? 10. And the v, well, it's 100 kilometers per hour, so that would be 100,000 meters per 3,600 seconds. Squared. So what did you get? Alright, so that is, what do we say, 46.2 kilowatts. Now, the next part is the efficiency is 40%? So, power out over power in times 100 equals 40. So what's the new power? What do we get? If you cross multiply, what do you get? 115 point, so 116 kilowatts. Yeah? Makes sense? The car is only roughly half as efficient, so now the engine needs to be twice as powerful to have the same result. Yeah?
Yeah.
Guys, does that make sense? Continue? Yeah. I want to do one at an angle. This pump one is a little tricky. I think I'll let you try the ones in the book to see. But I want to do one that's at an angle. I might do something like this one. No, that's a little hard. I'll make it a little bit different, okay? So, what I'll have here, we'll have a hill. And we'll say that this is at 30 degrees.
Yeah.
We'll put it, I don't know, we'll just make it, we'll keep it easy. We'll just say this is 1,000 kilograms. Okay? And oh, how hard do I want to make this? Well, it's going up the hill anyways. Oh, I'll make it pretty hard. It's going up the hill at a constant speed. So it's going up the hill at a constant speed. Okay? Is it accelerating up the hill? No. Constant speed up the hill. And my question is, oh, and you can assume as well the efficiency is 100%. No heat loss. Okay? My question is, what is the power of the engine? Yeah. I promised you it would be a hard one. Oh, okay. I'll give you one more piece of information. I'll give you the speed it travels at. I won't give you the time though. I'll say it goes at a speed of 2 meters per second. That makes it so much easier now, right? Any ideas? Any ideas? Will we have a look at it now? Will we do it? You think you got it, Marwan? Abdul Rahman? Alright, let's have a look at it. So look,
100?
there's a force acting down here, isn't there?
Yeah.
And how big is that force?
It's
1,000 G. Now what you can do is you can resolve it this direction and this direction. And there's also a force acting up. What's that? Reaction. Now that or was going to cancel this force, so we don't care about it. What is this force going to do? It wants to try and do what? Drag it back down, doesn't it? And this one here will be 1,000 G sine 30. because this angle here is 30 here. Okay? Now, why does this not fall down the hill? Well, there must be a force provided by the engine. How big is this force? Well, it's moving at a constant speed, so it's definitely not zero. How many cars go uphill with zero power engines? Not many. 1000 g sine 30. Why must it equal the balance? Yeah? So, let's calculate here. What does power equal? Work over time. Do we know work? No. We can work it out though. What's work equal to? Force times distance over time. Now, is this moving at constant speed? Yes. Can we use the distance speed time triangle then? Yes. What is distance over time? Speed. What's the speed? 2. What's the force? So this will equal 2000 g sine 30. I told you it was a hard one. So what do we get here? It is amazing, isn't it? Just truly amazing. What is it? 9810. So that's 9.81 kilowatt engine. Yeah. Now this is typical in physics though. It's not like there was lots of calculations. Were there? Were there lots of formulas used? No. In fact, I think it's fair to say we used very simple formulas. Yeah, I know. This is why you need to practice and have good diagrams. What's wrong, Jason? No. You can't accept this, is it?
Yeah,
Right, okay. Well, anyways, I wanted to finish with a hard example. So we have a few minutes left. For the last 5 minutes, you can get started on your power homework. Did anyone think they came close to getting this? Just the force. Huh? They wouldn't let me teach this if I didn't. I'm not just some guy that walked off the street saying, yeah, I'll give it a go. Sure, how hard could it be? No, so my degree is maths, but I took some of the physics subjects. And then my master's is maths and physics. So, yeah. I wouldn't say that. I wouldn't say that. Mathematician be a bit more accurate, but I did study a lot of theoretical physics. So this would be quantum mechanics, general relativity, stuff like this.
So you can make it count.
No, I haven't done the more mechanical, electronic kind of engineering. Okay, so I don't have your type of stuff, electric engineering. That's more experimental. That's more lab work, whereas mine has been more theoretical, like maths based. Yeah. So the stuff we're doing in class, this isn't really lab work. You know, we're not doing things like experiments yet. The experiments come in semester 2. So this first part of the course is a bit more theoretical. Yeah. All right.
So you're telling me that physics is a lot more harder than this?
Well, it depends what type of physics you do. You see, if you do theoretical physics, yeah, much harder than this. But if you do something like electronic engineering or something, civil engineering, it wouldn't be harder than this. Like, it would be as, at most it'd be as hard as this. When I talk to students who go on to do engineering, they tell me, oh yeah, their first year physics, you know, I was well prepared for it because I did the physics here. And I didn't really need to stress too much about it because we did all the stuff already. The same goes for their first year maths. They say, oh, the first year maths, very similar to what we did on the IFY. I didn't have to stress much about it, you know. So the level this is at is similar to first year physics. The only real difference in second, third and fourth year, I think, is you start focusing more on specialized topics. Like, you know what I mean? Like narrow in on particular topics. But it doesn't really get more difficult, it just gets more specific, specialized. And then you do more labs as well, experimentation. You know? You know, maybe I like teaching. Now, you might not think it from my reaction to this group sometimes, but you know, maybe on average I like teaching. Or maybe I just like to pay the bills. You know?
Your video is failed.
It did. I'll bring a USB key.